started?
Yep, live now.
Okay, so it's live.
You
Yeah,
want-
it says live, but then I can't.
Anything like that? That's the link. I mean, at the very least, at the possible least, yep, right. I think it's doing something. And
Oh, yeah.
yeah,
Well, yes.
yay. All right. So now you're gonna have time like me. Okay. All right.
Oh, yeah.
Yeah.
It's like where
Right.
you don't want to jump forward.
Okay. We'll be starting in just a second.
So it's semi-live.
Yeah, it's not like.
Probably just the volume. Testing, testing. You can hear me? Yeah, okay. All right. Oh, it's not live, right? So how's that gonna work?
Oh, yeah, so like.
Okay. We're good? Yeah, I think we're good, right? Probably you want to mute your speakers.
Well, I was just gonna, I mean, I guess.
Yeah, you can. Yeah. Okay, so welcome to the second day of BrainHack in Ann Arbor. Our Ignite speaker this morning is Moriah Thomason from Wayne University. And hopefully you can see that clearly on the screen. And I'll hand it over to her.
Thank you, I'm glad to be here. So human life begins here, and in fact, it begins even before this point. But until now, we've had little ability to measure function in the living human fetus. Now, resting state fMRI has sort of changed the game on that. We're now able to use functional imaging in utero to study healthy and atypical brain development. Now, it probably comes as no surprise to anybody here that motion poses a significant challenge. You cannot ask your fetus to remain still. But on the bright side, we've been doing this now for a couple of years, and we've learned a few key things, some of which make us optimistic that this is going to be a solvable problem. First of all, we now know on average how much the fetus moves. So right now you're looking at axial slices. You can kind of see an eyeball to give you reference. And we know now that if we acquire data, that there are times when the fetus remains still and times when the fetus moves. So you'll sort of, if you watch this video for a while, you'll see a demonstration of that. When the fetus is remaining still, we find that on average that period lasts about 70 seconds. So we're able to get about 70 seconds of periods where the fetus is still, and we end up tossing out about 40% of our data, which means that if I acquire a 9-minute fetal functional MRI scan using an abdominal coil, I can expect to retain on average about 160 time frames, which is sufficient with very low movement in those residual frames. So that's the strategy that we've used. Now, if motion didn't present enough of a problem, it's not the only challenge that we face in fetal fMRI. Most of you will see that this fetus is upside down and sideways and not in a normal orientation. None of our fetuses come in a fixed orientation and in fact may move. So when it comes to doing things that are standard in fMRI analysis, like co-registration of anatomical to functional images. This really does present a different type of paradigm. We also don't have atlases for automatic segmentation or registration processes. The fetal head is very small, and that obviously produces or introduces new challenges. And if that weren't enough, the fetus is encased within an independently moving maternal compartment. And finally, we have limited knowledge of the physiological basis of the signals that we are measuring. Despite this laundry list of concerns, this is an important area for development because we know that gaining understanding of functional circuit organization at the beginning of life is utterly essential. Neural development during this time is exceedingly rapid and more sensitive or vulnerable than at any other stage in the human lifespan. We're shaped in this time, yet we scarcely understand the functional processes at play, nor their relationship to future human health. The first resting state fMRI study was published by Veronica Schopf and colleagues. They were able to identify, using ICA, individual networks within individual cases. The gestational weeks are shown as numbers above the individual frames. We've carried out several studies over the last couple of years. This is a picture of one of our pregnant research participants about to go into our MRI scan. The first was published in Science Translational Medicine last year, and we were fortunate that that work was featured on the cover of the journal. We observed increased strength of cross-hemispheric connectivity with advancing age and also regional heterogeneity, supporting posterior to anterior and medial to lateral developmental gradients. These were observations that had been made previously using other techniques, but much more invasive techniques such as post-mortem samples and track tracing. So what we were really doing here as our first study was a proof of concept study, because this was the first fMRI study that performed group level analyses in functional fetal data. So it was important that we didn't totally go out of the box with our first study and instead try to demonstrate something where we have very strong predictions about what we should observe if our imaging method and our approach was working. Our next study came out in PLOS One earlier this year, and we found that activity, we used the graph theoretical approach. We found that activity in the posterior cingulate cortex became more natively correlated with other brain regions with advancing age, and we also observed decreases in modularity. Our third study just came out, I think, this month in cognitive developmental neuroscience. We looked at many different networks using a seed-based approach and divided fetuses into a young, middle, and older age group. And our new observations in this study were that increased cortical-subcortical connectivity and greater long-range connectivity characterized development in the human fetus. So that brings us to why we're here today, which is to really look a little bit at the processing that we use to get these data, not so much the results themselves. So what I'm showing here is a schematic of your standard graph analysis, but what we're going to focus on today is, let me just change frames for a second so I can show you, is we're going to focus sort of in this area, which is how I get to the point that I have these very nice looking, very stable, you can assume, images that will yield good data. Because it actually takes a lot of work to get to this stage. These are smooth, normalized, registered to a 32-week template, fetal template, functional images that are like what you would obtain straight off the scanner in a child or adult. They are subject to, we use Cameron-Crowder's spatial spectral clustering method. We extract time courses from 150 different regions. We regress CSF, white matter signals in motion to get your standard connectivity matrix, upon which we perform standard analyses. So none of the right side of this is a mystery, but the left side is, because the left side is where we're really trying to innovate and move the field forward so that we can allow fetal images to be used much to the same extent, to the full extent that our other brain image data are used. So earlier I told you that there are periods of stability and periods of movement. Anyone that looks at what the axes are on these translational and rotational plots should be shocked and disgusted and dismayed, because this is obviously an extraordinarily large amount of movement that we cannot deal with. But as I told you, there are periods of relative stability in these data. And I'm just going to switch views for a second again. where you can see, for example, in the later half of the scan, that this fetus remained relatively still. So the strategy that we've used is to analyze only those periods in which the fetus is still. So for example, if you look here, you see areas, you see times in which the fetus is remaining relatively still here on the left, and the areas that are shaded in gray, if that's coming through. Is it coming through? Oh, right, okay, it might come through. Are periods in which the fetus is. I'm gonna make a quick adjustment on my display, so give me a second. I guess I don't have the option to zoom and draw. Right, I've limited ability. I'll proceed. So if we just analyze those frames that are shaded, so sort of indicated here above with A's and B's on run 1 and A and B on run 2, then what we need to do is we need to take our raw data. So we need to take the raw data here, and we need to draw individual masks, 3-dimensional masks. But the interesting thing is that we can't just draw one mask for a given fetus. We have to, in fact, draw as many masks as there were periods of stability. Because the fetus does tend to stay in one position, it favors a certain position, but even if the head rotates by a couple of degrees or millimeters, we need to create individual masks for each of those epochs. And herein lies the major slowdown in our analysis, because we have to generate these individual masks. Each subject may need 10 masks for 2 different fMRI runs, and those masks and the quality checking involved take 30 to 40 hours per case, because there are no existing segmentation tools that are capable of extracting the fetal brain cleanly and easily from the MRI, from the maternal tissue and the surrounding tissues. The rest of it's pretty straightforward. Once we've extracted it, we reorient it into the normal position, and we're able to normalize it to a fetal template. And it looks a lot more like what you're all used to seeing. So we've come up with a solution, which is working with Roberto Toro, a researcher at the Human Genetics and Cognitive Function Lab Neuroscience Department in France. And so I'm going to just do a little demonstration of what I've been working on with Roberto. So our idea is that it would be possible to save a good deal of time and crowdsource our efforts. So in his brain catalog, he has several different species of animal, and we've put in one of our fetal functional MRI data sets raw. In this case, we're just selecting a single volume that's in the middle of a lot of stable volumes that would be ideal to trace. And this is a website that you could all go to today and try looking at. But in order to edit this, you would have to have an account. So I'm just going to log in. So here we see, and it is dark, I apologize, I tried to change this before today, but here is an axial fetal brain. So just a single 3D volume, an EPI volume, so it's not necessarily detailed. But hopefully you can see that circle and see that it's terribly dark. So chances are you can't see that circle. But if I would like to edit it, I can go ahead and I can trace directly on the image. I see that it's not coming out right now, but hopefully the point is made that this would be a means for multiple people to edit a single image concurrently. So that means that all of us could be logging into a single MRI images, and in a matter of moments would be able to generate a mask that would be able to that we'd be able to edit. So the question for us, one of many, as we think about moving forward to a crowdsourcing approach, is how exactly are we going to execute this plan? So there are precedent for the type of thing that we're trying to do here, which is we would like to try the idea that we could take some of the time out of our process by using the public as a crowdsourcing basis for tracing these fetal brain images. So there is a history of this. I point out first Rosetta at Home, which is the one that most of you are probably familiar with, which is protein folding. But I found an interesting point, which is that individuals using Rosetta at Home became frustrated with the program when they realized they could see ways of solving the problem, but they couldn't interact with the program. And the researchers hoped that humans would be able to improve the attempts of computers to solve problems. So, it will be a great advance for fetal functional imaging if we're able to do this in an automated way. But I find it interesting that a population of people bring knowledge to the table that a computer program wouldn't necessarily have the capability to converge on. Another example of this is iWire, which is a program out of MIT, I believe directed by Sebastian Sun, that uses the user's trace a neuron's path by coloring each axon. So I would consider this maybe one of the best examples in neuroscience. So we're not quite sure how this is going to work. We don't know what our distribution channels will be. Will we launch websites as these individuals have done? Will we draw people to the websites? Will we utilize existing communities to pull people onto these channels that we devise? I don't know. And it's kind of one of the reasons I wanted to be here today is to see what people think. I mean, this is an idea at this point. So any feedback that people would want to give or any ideas. I didn't put actually I might have put my email up. If there's anybody that wants to email me or talk about this, I'd be very interested to hear what people think might work, both on distribution, I think, and on quality assurance. One point I want to make before I let you go on that last piece, which is the quality assurance. These individuals would be creating a mask, a binary mask that would be then saved directly from the site. And then that mask could easily be checked and tested before it's applied to our data in our lab. So it's not as if they're going to be working directly with our data. They'll be generating something new that we could potentially use. So there's lots of opportunity for quality assurance in this process. That's all I've got for you.
Okay, thank you.
Thanks very much.
Why don't we'll put her email address on the website.
Yep.
And make it like a frame